numbers. This chapter 3 is about experimental error. So now section 4 is about propagating uncertainty from random error. For most experiments, we may need to perform some arithmetic calculations on several numbers, and each number has a random error. Then the uncertainty in the result is not simply the total individual error, because some are positive, some negative. They can cancel somewhat. So how the result error or uncertainty depends on the operation. So addition, subtraction for the same rule. For example, we have 3 numbers. Like you read volume from Burette, or you read math from balance. Let's see, 3 readings. Is there uncertainty? Uncertainty means some random error. Three reading uncertainty like this: 1.76 plus minus 0.03 random error plus minus. And the result is first number plus second number 1.89. Random error is 0.02. Minus third number is 0.59. Random error is 0.02. Now what is the result? The result itself, you just use calculator, very easy. 3.06. The question is uncertainty error 4. So we need to figure out E4. Let's say this label as E1. So E1 is 0.03, E2 0.02, E3 0.02. Then the E4 equals to E1 squared plus E2 squared plus E3 square root. So the actual number is 0.03 squared, 0.02 squared plus 0.02 squared. Then square root equal to 0.041. This 1 is extra digit, or the first insignificant figure. Normally keep extra 1 before the final result. So final result looks like this. Your last digit is 0.01, second decimal place. So should be just keep after here.
Would you say that 1 was a 0.04 to the 1?
This 1
Yeah.
is the first insignificant figure. This is actual because the initial number is only up to here, right? 1, 2, 1, 2, 1, 2. And this is a 1, 2, 3. 3 is the first insignificant figure. Okay. Normally, it's before the final result, we keep one more digit. This is the first insignificant figure. If you have actual calculations, so if we just delete here, will cause actual error. But if this is last step, we just delete it. Okay, of course, if this is 5 or above 5, we need to round up. So your answer will be 3.06 plus minus 0.04. Plus minus 0.04. 0.04 is a uncertainty about the result. Okay, are you okay? This is multiple, no, this is addition or subtraction. Results arrow is add all these squares together as square root. So no matter it's minus or plus, you always add them together. Then multiplication division for the different rule with addition subtraction. So multiplication division for the same rule but different with addition subtraction. So the rule is we need to convert all uncertainty to the relative uncertainty. Convert all uncertainty to relative convert all uncertainty to relative uncertainties. Let's say example. We still use these three readings as example, but this time the operation is multiplication division. 1.76 multiplied by 1.89 divided by 0.59. Again, the number inside the parentheses means the uncertainty or random error. The result itself is use your calculator 1.76 times 1.89 divided by 0.59. Result will be 5.64. This 4 again is the first insignificant figure. If this is not the final answer, we should keep actual one digit. If this is the final answer, we could decide 4 and below 4, just delete it. 5 and above 5, round up. Okay. The question is the uncertainty, the result, random error. This time, what is E4? So first, we need to convert all uncertainties to relative uncertainty. So this is E1. So E1 is absolute uncertainty 0.03. Convert to relative uncertainty, use percentage. So absolute uncertainty divided by its actual value times 100%. This is relative uncertainty. This one, 1.7%. E2, 0.02 divided by 1.89. Similarly, order to relative uncertainty is 1.1%. Then E3, 0.02 over 0.59 times 100. This will be 3.4%. So again, this second digit is actual. You remember we learned this already in Q1, right? Because division, multiplication, answer cannot have more significant than n of the original number. This original number only one significant. This zero is not. Zero after decimal point before first non-zero digit is not significant. This is only one. This is three. So answer can only keep one. The why we keep 1.7, this is 7 is actual. Because this number may not be the final answer. So we need to keep one actual digit. Otherwise, every time you delete or run up after several operations, your answer will be have very big error. Okay. So always keep one actual digit before the final, before your final result. Similarly, this one is same, right? Because this only one we keep two. This only one we keep two because this is not the final answer. Okay, so first convert this uncertainty to the relative uncertainty. Then we calculate the resulting uncertainty. Resulting uncertainty, actually more accurately, this should be percent, right? Error what is percent? Will be E1% squared plus E2% squared plus E3% and 7%, 1.1% squared, 3.4% squared. Add them together, square root. This is the 4.0%. Okay. So similarly, this is 0 also actual digit. This is insignificant figure. So these are same first insignificant or one actual digit. Similar as here. Then your answer will be 5.64 plus minus 4.0%. Since now is the final answer, so we need to think about how many digits or significant figure we we should keep because initially gave us is this operation, right? This number times this number divided by this number. The answer should keep how many significant figure? Division, multiplication, answer is significant figure, right? Addition, subtracting is digit to the right of decimal place. So this is answer we need to think about significant figure, not how many place of the decimal point. Significant figure, this three, this three, this two. Answer can only have two. Answer cannot have more significant figure than any of the original number. Since this only two, the answer only have two. 1, 2. So this one is not. This is first insignificant, right? Since this is 4, less than 5, we just delete it. Plus minus should be inside is for instance. Then what is wrong? What is uncertainty? No, this is relative. We need to convert back to this absolute format. Okay. So how to convert the absolute format? Since we convert the relative like this, absolute error divided by the actual value times 100%, you get a relative. Then relative times the value back to absolute error. So this E4, instead of percent of E4, should be your answer is 5.64 times. Again, this is 5.64. We'll still keep this extra digit because this is not a final answer. Times this percent error. Percent error is 4.0%, right? Use calculator. 5.64 times 4%. Still keep extra. Because this is not a final answer yet. So we need this give you a number is 0.23. Value times the relative is absolute. Absolute error. So value times percent, you get absolute error. Absolute error is not accurate. This is still random error because this is just the absolute uncertainty. It doesn't confuse. We have several different concepts. Random error, systematic error. Plus minus, this means random error. But this is absolute uncertainty. This means it could be 0.03 larger than this, or could it be 0.03 smaller than this? But 0.03 is the absolute value. It's error. So we absolute error divided by actual value, and 100%, this becomes relative error. Then relative error times the actual value will be absolute error. Okay. Here, so value times relative error back to absolute error. So absolute error, things now we know this is insignificant. Now here is the final answer. We don't need a cap. So this 4 is below 5, just delete it. Then how many significant figures should we keep for the absolute error? You can simply take it just look here. So this actually only one significant because our initial absolute error is a one significant figure. So finally, there's one, because this means this is the first insanity figure. Then this is also the first insanity figure. So finally, it's plus or minus 0.2. Okay. Most case in this class, that's all. Plus and minus multiplication division. Occasionally, we have log and anti-log. Log is like a pH. Convert hydrogen ion concentration into pH is log. This is occasionally. So for log and anti-log, we're not sure here. Just read the textbook, page 61 to 62. The rule for log and anti-log. If the operation is a mix, you have multiplication, division, and then you have addition and subtraction. There's a mixed operation. Read the textbook 58 to 59. Just follow the rule we just learned. Whatever operation you take, follow that rule. When you do addition, subtraction, follow this rule. When you do multiplication, division, follow this rule. Okay, that's it for the section 4. Then section 5 is about the propagation of certainty of uncertainty from systematic error. So far it's a random error. Sometime during the experiment you could have systematic error. Of course, we don't want this happen. The systematic error, we can find out the reason, then we can make correction. So propagation of uncertainty. Systematic error. Systematic error is treated in a different way from that of a random error we just learned in calculation. Just simply get the total systematic error for each individual number, because systematic error cannot be cancelled, always the same direction, either or positive or negative. Different way. Let's see an example. If actual measurement looks like this, A plus alpha, B plus beta, C plus gamma. So alpha, beta, gamma are the error. Absolute error. Here's a systematic error, right? Absolute systematic error. Some book called determinate error. Then result in this format, R plus log. Log is a resulting error in result. Log is a resulting error. R is a result. Okay. So as I say, this directly from the operation. So if R come from A plus B minus C, then law also follow the same law, equals R plus beta minus gamma, follow the same law, right? Your result is plus, then your error also plus. Your result is a minus, then error also minus. All the same rule. Absolute error transit directly. Transit into result directly. Result is plus, error also plus. Result is minus, error also minus. Or if results come from multiplication division, then the error translated into result is that you need to convert error into relative error. Alpha divided by A, similar as here. Alpha error divided by the value becomes a relative error. Alpha is the error from A, as alpha divided by A is a relative error. Then if multiplication, then error is plus. So beta divided by B. Here for these two are different. This is beta is error. This is B is the actual value. If division, then the error is minus. So gamma divided by C. So this time the relative errors transit into results. Okay, this is the difference. Convert absolute error to relative error. Absolute error divided by value. If multiplication, then error is addition. If division, then error is minus. That's it for the chapter 3. Then we'll start chapter 4. Here is chapter 4's homework. Two weeks from today. Again, this exercise just let you understand and either complete this problem. So exercise has detailed explanation. You are not required to turn it. To read this exercise and start to work on this. Problems are required to turn it. Chapter 4 is about statistics. Okay. So in the lab, do an experiment. We need to repeat several times. And the experiment, we cannot just run one measurement. Let's see. Not very easy to move the mouse. I don't recognize this. This flash driver works fine on my computer, but they're not recognized by this. Do we have any place we can plug in here? Let's see, can we plug in here? Yeah. Okay. Yeah. This is this experiment is if we have 50 coins, each coin you have two sides, and if we toss on a surface, 50% hit, another 50% the back side, and if we have 50 coins tossed in the same time, we expect 25 hit on. The other 25 hit the backside on, right? And this, if we toss 20 times, here is the result. Toss 20 times, this is 5, right? This means there are 5 times about 28 is hit on. Right, this is 30, 29, 28. And 5 times is 25, this is 4 actually, 4 times. And 3 times is 29 coins hit on. 2 times is 23 hit on. Another 2 times is 26 is hit on. And one times one times is this may be 18. This is 20. It's 19 or 18 coins with hit on. One times 24 hit on. Another one times 21, 31 or 32. This is 33. So this is bar. This each bar tell you how many times, how many coins hit on. So this smooth curve is we call Gauss curve. Theoretically, we expect most of the time, if 50 coins, should be 25 coins with hit on. 25 is hit on backside. So bar curve and this Gauss curve, big difference. But if we calculate the average, this is mean value, this is 26.6. This means if we only toss 20 times, 20 toss 26.6 times, or 26.6 times is hit on. Okay. So actual value is these two. If we toss 400 times, then all these bar graph pretty close or much closer than the smooth curve. Okay, so this is big arrow, but this is much smaller arrow. So if we run like 1,000 times toss, then the bar graph will be much closer to this smooth curve. This smooth curve is mathematically should look like this. Okay, so maximum point 24.98. So everybody know 50 coins, so 50% should be tossed on. 50% means 25 coins. And here is 24.98. If we only toss 20 times, then you see this average is 26.6. This is little far from 25. This is much closer than 25. If we run 1,000 times or 2,000 times, maybe we can reach 24.99 or 24.999. So you repeat more, your average is closer to the theoretical value, or here is true value. Anyway, can you understand this figure? The main idea is you repeat more, the average value will be closer to the theoretical value, which is a true value. If you run only one time, then this 50 coins may be only, here shows, only 18 coins with hit off. The other 32 is hit. So that's why for any experiment, we cannot just make one experiment. For any sample, we need to repeat. Of course, we cannot repeat 1,000 times or 2,000 times. We don't have so much time, right? So in the lab, I require everybody repeat at least 3 times. That is minimal. So here also tell us the mean value or the average. We use X bar. X bar means mean or the average. Okay. Average value. We give a name. Mean value. X bar come from x1 plus x2 up to whatever you repeat xn divided by the number of times you repeat. Mathematically, this we can use sigma from 1 to n sigma I sigma xi divided by n. In math, sigma means summation. Sum, yes. So xi is the each measured value. N is the number of measurements. So this is the average mean value. So you just add all measured value divided by how many times you measured. New concept here is a standard deviation. Yes. So this defined as sigma xi minus x bar squared divided by m minus 1, then square root. What this means? Xi is each individual measure value minus x bar, which is the mean value. So each individual measure value minus the average give a square. then add them together, sigma is sum, right? Divided by n minus 1, then square root. So this or standard deviation. Then standard deviation, what this means? The standard deviation measure how closely the data are clustered about the mean value. The smaller the s means all measured value close together to the to the mean value. The smaller the s, this means the more closely the data are clustered. Around the mean value. Okay. And very easy to move. No response. We can move this way, okay. Here we have two curves, right? Black one and a green one. Right? So black curve shows this smaller s. Green curve represent a larger s. So if it's indefinite, this black curve means measured value more clustered around the true value this. And this green curve with larger s means scattered far from the true value. Okay. So during the experiment, we hope the smaller standard deviation means your precision is better. Because precision represents how closely are your measured value to each other. If scattered far away from each other, then your curve very fat, like the green colored curve shows bad precision. Okay. Yeah, it's time. Let's stop here.